Hello, I'm Past Paper Guy. I'm going to be solving the Electronics Unit 2 GCSE by WJEC from 2016. As with all my videos, I suggest that you download the paper. There's a link in the comment below, and you have a go first before you watch this video. Right, question 1. All boxes on the left give the name of two subsystems, boxes on the right descriptions of the applications. Draw a line to link each subsystem to its correct application. So we have something that goes once, something that goes lots of times. When a burglar alarm is switched on, a warning LED flashes on and off repeatedly. So that's the key word, repeatedly there. So that's the A stable. Street light comes on when it gets dark and turns off when it's light. Not really. Buzzer in a shop comes on for 10 seconds. So there we go. That one will be the monostable. There are 4 signals generated by monostables. Just quickly check the scales. They're all the same time scale, but they're not the same voltage scale. Which one has the longest period? So that'll be the one that's widest, this one, which is 2 seconds. So that's D. And which signal has the largest amplitude? It's the one that's tallest, which is this one, 12 volts here. Compared with all of those, so it's C. Okay. Question 2. One of the following circuits is an A stable, one is a latch and one's a monostable. So you should be able to recognise these. This is the A stable with 2 resistors and a capacitor and a timing chain. This is the monostable with the trigger and 1 resistor and 1 capacitor. And this is the latch. So it's A, which which one is the A stable is A. Here are 3 A stable signals. Check the times are the same, the voltages are the same. Which has the highest frequency? So the scales are the same, so it's whichever one goes the most times. So it's going to be C, has the highest frequency. What's the amplitude of signal A? So the amplitude is the height of the box here, so that's 1, 2, 3 volts, because each one of these is 1 volt. So 3 volts. Question 3. The circuit diagram shows a time delay circuit. When the switch is closed, the output stays at a high voltage for a while and then drops to a lower value. Right, so what's happening here is when you close the circuit, this value here, the voltage across the capacitor, charges up. So it starts fast and slows down. Right, so because this is a NOT gate, then at about that value there, so that's the voltage and that's time going across there, then the output, so that's VC there, the output will do that. So it would be, when this is at 0, this will be high at plus 12 volts, and when this is at it goes above about 6 volts, it'll go low. So which one of the following sets of resistor and capacitors give the output for the longest time? So the time period of this is R times by C times by 0.7 is how long it would take to get charge halfway. So we just want the biggest values of these. So this is going to be the biggest values. They're going to times together to make the biggest number. Which one of the following statements gives the best explanation for the purpose of a NOT gate in the circuit? Without the NOT gate, the time delay would be much shorter. No, it doesn't make any sense. It produces an analog output voltage. Well, it definitely doesn't. It produces a digital output voltage. It ensures that the output current does not affect the time delay, and it inverts the signal from the switch. Well, inverting the signal isn't really an important part. What's important is that if you were to take any current off here, that would discharge the capacitor. So it's this one. It ensures the output current does not affect the time delay. Because as you take current off the capacitor, you would reduce the voltage VC, so it wouldn't charge up as much. Current would instead flow this way. A NOT gate doesn't require any current to trigger, so it doesn't take current going in that way there. Which of the following statements describes the action of the rising edge trigger D-type flip-flop? When the clock signal rises from a 0 to a 1, then data is copied through to Q is what we want. The Q output copies the clock, no. The Q output copies the logic level present at the data input. There we go. A rising edge triggered D-type flip-flop receives the clock and data signals shown in the graphs. Complete the graphs to show Q and Q bar. Q starts at logical 0. Okay, so the first thing we do here is we mark on our rising edges. It makes it a lot easier. Then we just need to copy those down. There, 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 and there. Okay, so here Q checks what D is whenever we get one of these dotted lines, whenever we get a rising edge. So D here is 1, so Q is going to go up to 1. And it's going to stay that way until the next dotted line, and it's going to check here. It's going to be 1 again, so it's going to stay at 1. It's going to be 1 again, so it stays at 1. And then here it's 0, data is 0 when we get the rising edge, so Q goes to 0 like that, and the Q bar will be the inverse of that. 1, 2, 3, up there and along there. And that is that one. Here's a block diagram for a single digit decimal counting system. We have a switch, a BCD counter, some subsystem X, and then the 7-seg display here. Which of the following is the best reason for using a BCD counter for this thing? So if we have a 7-seg display, it can only display the numbers 0 to 9. A binary counter goes from 0, 0, 0, 0 to 1, 1, 1, 1, which is 0 to 15 in decimal. So BCD, a BCD counter goes from 0, 0, 0, 0 to 1, 0, 0, 1, which is the numbers 0 to 9. It's binary coded decimal. So we want it, it's because it only displays numbers 0 to 9, so which one describes this? Simplest, so that's just nonsense. Systems based on a decimal numbering system. Yes. System automatically resets on the 10th pulse. Yes, the system displays only 1 digit. Well, we're after why we use a BCD counter. I think this one best describes it. Well, that's not a... I think that one best describes it. It resets on the 10th pulse because it goes 0 to 9, and then on the 10th pulse it resets. Which of the following subsystems is for X? So we want to know what this is here. Nope, it's not a comparator, it's not a transducer driver, it's a decoder to turn the BCD number into the one that lights up these, the correct sequence of these. A logical 1 makes the segment light up. Okay, we need to put 0s and 1s to make a 3. So we're going to need that one to be lit up, that one to be lit up, that one to be lit up, that one, and that one. So we need A, B, C, D, and G, and the other 2 need to be 0s. Question 6. The boxes on the left give names of 2 interface devices. The boxes on the right give 3 descriptions. Draw a line from each device to its correct description. A comparator and a Schmitt trigger. So a Schmitt trigger has 2 fixed switching thresholds. A comparator has 1 threshold which can be changed easily and has 1 fixed switching threshold of 0.7 volts. Now that's kind of how either a transistor would turn on or a diode. Question 7. Here's the flowchart for parts of a control system. So we've got a decision here, looping back, a decision here, looping back, and a process here and a process here. This part of the system waits until a switch is pressed. So this is it waiting for it to be pressed. Then it adds 1 to a variable called total. so that's that. Then it checks to see if the total has reached 12. If it has, it resets the counter, and if it hasn't, it goes back. So that returns that way, like so. Excuse my writing. The flowchart contains 4 instructions. Instruction A is total equal to 12, is the switch pressed, is it, etc. Right. Which of the following instructions is found in box P? So we is here, wait till the switch has been pressed, so we want is the switch pressed, so that's B. Which of the following instructions is found in Q? So that's total equals total plus 1, so add 1 to the total, so that's instruction C. Which of the instructions can be found in box R? That's is the total equal to 12, so that's instruction A. There we go. Right, question 8. This is the standard block diagram for the mixer that you need to learn. The subsystems in this are written here. Which subsystem turns sound into electrical signals? So those are microphones. Boosts the current, that's the power amplifier. So that's boosting the current for the loudspeaker. The preamps boost the voltage from the microphones before you put them in the mixer. Combines the signal from a number of sources. As you can tell from the diagram, it's the mixer. The diagram shows a D-type flip-flop used as a divide by 2 subsystem. Okay, so I've got standard ripple counter with Q bar going back to D there. Output Q generates a frequency of 20 Hz. So if that's 20 Hz, then that must be 40 Hz there. What is the frequency signal at the clock? That's got to be 40 Hz because it's divided by 2 to get to there. And here, this one here is exactly the same frequency as that. It's just upside down, that's all. So that's got to be 20 Hz there. Question 10, we have an amplifier here, and what's the gain? Well, the gain is equal to V out over V in, which is equal to 30 times 10 to the minus 3 divided by 2 times 10 to the minus 3, which gives you 15. That's 15 times bigger than that. Here we have a non-inverting amplifier. So the non-inverting amplifier equation is that the gain is equal to 1 plus R feedback divided by R2. Now you can tell it's a non-inverting amplifier because the input here, which they haven't labelled, goes into the non-inverting terminal there. So if we want this number to equal 10, then from these values here, we want this one to be 9 and this one to be 1, so that we have 1 plus 9 over 1, which will give us a total of 10. So it's that one there. This is them trying to trick you, because if you did that, you'd add the 1 and you get 11. Same with that one, and that one you get 11, and then you'd add 1 and you get 12. So it's this one here. The signal shown in the graph is applied to an amplifier having a voltage gain of 20. What's the amplitude of the output signal? So they're giving you the units of millivolts, so you don't have to be careful about that. The amplitude of this signal is 2 volts. So if we times it by a gain of 20, we get 40 millivolts. That's the distance from there to there is the amplitude, 2 millivolts. Question 11. A light sequence controller uses a simple memory IC to control a number of LEDs. The memory IC has 4 addresses and 3 data pins. A logical 1 from the memory IC output causes the corresponding LED to light. Okay, most of that is irrelevant to the actual question. Complete the statement. The pulse generator has a period of so many seconds. So T is equal to 1 over F is equal to 1 divided by 0.5. So that is 2 seconds. 2 seconds. Complete this statement by circling the correct answer below. The pulses applied to A1 have a period of so many seconds. Right, so it's not this A here, it's this one here, A1. So that is B on the counter. So if the frequency here is 0.5 Hertz, then the frequency here is going to be 0.25 Hertz, because every input on the count, every output on the counter will be half the frequency. So here it will be so it'll be 0.125 Hertz. So it'll be a quarter the frequency. If it's a quarter the frequency, that means it's 4 times the period, so it will be 8. Okay, and this is the bit that's not really on spec anymore, but you can guess it really easily. You've got 4 memory lines, which means you've got 2 to the power 4 memory locations, so that's equal to 16. So you've got the number 0, 0, 0, 0, all the way down to 1, 1, 1, 1, which is the number 0 to the number 15. And so that's 16 numbers, because you've got 0 as well. So it's one of these two. And then each storing a 3-bit number. It even tells you that there are 3 data pins there, so each one stores a 3-bit number. Yeah. So it's that one there. A 3-bit number which could have 8 possible values, which is why they've put that red herring in there. Question 12. A 2-bit counter is falling edge triggered, so that's important there. You can see that it's falling edge triggered from the diagram. It's got that little circle there. Oops, that little circle there means that it's falling edge triggered. So we want to draw arrows down on the falling edges, here, here, and here. So we can extend these lines down like so. Now the binary values that we're going to count are these, because it is a counter, and we've got to think at this one, this falling edge here, the least significant bit is going to be A, so that's going to change at this falling edge here. The most significant bit won't change just yet. Then at this one, the least significant bit will change. Then at this one, the least significant bit will change here. And then on this falling edge here, the most significant bit will change. So the most significant bit goes here, and then here. Now if you think about what this represents, in logic, you've got a 0 there and a 0 there, which is that one. Here you have a 1 here and a 0 here, which is that one. So this is A and this is B on this. Here we have a 1 on B and a 0 on A, and here we have a 1 on A and a 1 on B. Question 13. Here's the block diagram for a latch. You've got your trigger input, reset, and an output. The latch system is initially reset. It's triggered at time X and reset at time Y. Complete the time diagram. This seems very easy. It's triggered at time X, stays high, it's reset at time Y, so it goes along like that. The diagram shows the incomplete circuit for the latch based on a rising edge triggered D-type flip-flop. Switch Z is used to trigger the latch, W is used to reset it. The buzzer sounds when the latch is triggered, so it triggers, we need it to trigger so that it goes high when this button's pushed in order to make that buzzer come on. So we need the D to be connected high. This will go to there. That'll cause the rising edge when you click it, and then the reset line here comes from there. So we just need to put these into these now. 3 connections are needed for the circuit. A must be connected to clock. B must be connected to reset, and D must be connected to the positive power rail. Question 14. The diagram shows part of a light sequence controller circuit for 3 LEDs, red, yellow and green here. The LED lights when it receives a logical 1. So we've got a pulse generator, a counter here, 3-bit counter with its outputs, and we've got some logic gates here and a reset line. Okay, the reset line might come into play down here. Here's our table. I think we'll leave this for the moment. So, which one of the following would make the counter reset on a pulse of 4? Well, to reset on pulse 4, we're going to want this counter to be at 4. So it's got to be 1, 0, 0, like so. And we want it to reset back to 0, 0, 0. So I'm just going to write in the remaining value there. So this is the value of the outputs on the 4th pulse. So we notice that C has just gone high. So to reset, we would connect C to reset there. So connect C directly to reset. Complete the C, B and A columns for the truth table by adding 0 or 1 to show the counter outputs when pulse 3 has arrived. Okay, well we did that. It's funny that they ask them in that order. It would be easier to have done that one first. Anyway, complete the red, yellow and green columns by writing either on or off. Okay, so let's do red first. So red is just the same as B. So that's off, off, on, on. Yellow is not C, so it's the opposite of that, so it's always on. And green is the AND of B and A, so that one is on. Those two are off. Okay. So just check that, A and B, that one and that one. That yellow is not C, which is always on, and red is just whatever B is, which is off, off, on, on. Yeah. Question 15. The graph shows the way in which a voltage gain of an amplifier changes the frequency of the signal changes. Right. So for the bandwidth, you need to know your definition of bandwidth, which is when the voltage gain is 70% or more of its highest value. So here we've got 100, so 70% of 100 is there, which is the same as 70. Nice easy numbers for you here. So we go along there, we go down there, and lo and behold it comes out at 3 kilohertz exactly. Nice and straightforward. Tick one of the following that could increase the bandwidth but leave the voltage gain unchanged. Use a higher power supply voltage, not really. Increase the amplitude of the input signal. Combine several amplifiers in a multi-stage amplifier, that's the one. Replace the amplifier with a non-inverting amplifier. No, none of those will help you. You want to cascade amplifiers together. So if you had a times 10 one and a times 10 one instead of a times 100 one, these would each have bigger bandwidth, 10 times as much in fact, as this one. So you'd increase the bandwidth to 30 kilohertz in that case. Question 16. A non-inverting amplifier has a voltage gain of 40. The upper graph shows its input signal. There's its output signal. Notice it's got some clipping distortion here because it's been amplified too much and it's gone above the power rails. Name the effect illustrated in the graphs. I assume that's what they want, clipping distortion. Which of the following could eliminate this problem? Reduce the voltage gain on the amplifier, well that would work. Increase the voltage gain of the amplifier, no, that would make it worse. Reduce the bandwidth of the amplifier, that would have no real effect. Increase the bandwidth, no. It's not a bandwidth problem, it's that you're hitting the power rails here. So you can reduce the gain or increase the power rails, so it's that one there. Question 17. An inverting amplifier has a voltage gain of 40. The input signal has an amplitude of 0.2 volts and a period of 1 millisecond. Draw the wave on the graph below so that it shows the corresponding output signal. Right, so if the input signal is like that, then the output signal is going to be like that. Now, I don't think it matters where you start on a question like this, so we just need to work out what the amplitude is going to be. The amplitude is going to be the gain is equal to V out over V in, so V out by the gain, which is equal to 0.2 times by 40, yeah, that's 8, isn't it? So it's going to peak at 8 volts. It has a period of 1 millisecond, so that's one full wave is going to take that long there. So half of the wave will be here, so it's going to go through that point. So if it starts here, it's going to go through that point. I'm going to make it go down to start with, just because I don't think it can't matter, but because it doesn't draw you the original wave. So we want it to go down to -8, and that halfway between here and here is halfway there, so it's going to go through that point there, and then here, halfway between here and here, it's going to get up to that point there, and then it's going to do the same over here, so that's one more full wave, so that's half a wave there, halfway between here and here is going to be there, and that's at -8, and halfway between here and here is going to be there. Right, so the easiest way to do this now is to turn your paper on its side and draw like so. Right, now one of the advantages of drawing these little crosses here, here and here is that even if your wave doesn't look very wavy, it's still clear to the examiner that you are trying to get it through these points here. So we've got a time period of 1 millisecond, so there's the time period of 1 millisecond, and we've got an amplitude of 8 volts, so there's the amplitude of 8 volts. Okay. 3. Question 18. The block diagram shows a system used to count how many times a switch is pressed. Explain why it's necessary to debounce the switch. If you think a switch being pushed might go through several bounces, and if you count the rising edges here, then even though you're pushing the switch just once, you would count, in this example, 3 rising edges. So why is it necessary? So the counter only counts once for every switch press, not each bounce. Part B, the debounce circuit contains a Schmitt inverter. Here we go. Performance of a Schmitt inverter is shown below. So this is the input, there's the output. So we're going to need to find the switching thresholds. So the first thing to do is just to draw a dotted line from there and from there. So one of the switching thresholds is 3, and one of the switching thresholds is 1.5 volts. So the output of the Schmitt inverter changes from a logical 1 to a logical 0 when the rising voltage reaches 3 volts. And the output of the Schmitt inverter changes from a 0 to a 1 when the falling voltage reaches 1.5 volts. Last question, 19, it's got the transistor in here. So a signal from a logic gate switches from 0.5 volts to 7.7 volts. Complete the table by adding the correct voltages for V1. So when this is at 0.5 volts, this does not reach the 0.7 required to turn the transistor on. So no current flows from there to there. If no current flows from there to there, then no current flows from there to there. So there's no voltage drop across that resistor. So this is 0.5 volts. Lots of people say 0 volts here because they think the transistor's off, that must be 0. No. No current is passing through there. So this voltage here, which is at 0.5, is the same as that. And when this is on here at 7.7, then this transistor will be on, so V1 will be 0.7 volts. The state of the lamp, off, on. The bulb in the lamp circuit is rated at 12 volts, 100 milliamps. The transistor has a current gain HFE of 50. Calculate the base current when the transistor is just saturated. So when it's just saturated, then that means the voltage drop across there is equal to 0 volts. So that means you've got 12 volts across there. So if we've got 12 volts across there, we've got 100 milliamps going that way. So we need this equation here, which is that I collector is equal to I base times by HFE, like so. So the base current will be IC over HFE, which is equal to 100 milliamps divided by 50, it's 2 milliamps. 2 milliamps. The logic gate outputs 7.7 volts. The transistor is just saturated. What is the voltage drop across the resistor R? Well, the voltage drop across this resistor, it's got 7.7 on this side, 0.7 on that side, so that's 7.7. Take away 0.7 equals 7 volts. Hence calculate the value of R. So R is equal to V over I, which is equal to 7 divided by 2 times 10 to the minus 3. It's 3,500. Oh, it wants it in kilo ohms, so we need a decimal point there. And that's the end of paper 2. Thank you for watching. Good luck in your exams.